Johnstown, Pennsylvania, May 31st, 1889, 4:07 in the afternoon. At the moment, the South Fork Dam burst. 20 million tons of water cascaded down the Conemaugh Valley at nearly 40 miles per hour. Within minutes, 1,600 structures vanished, yet 37 remained upright on their original stones. U.S. Army Corps engineers mapping the ruins that June recorded a single common factor. Each survivor's foundation cut at least 7 feet into undisturbed blue subclay. Builders had long mocked such digging as old country waste. But when the Johnstown Water Company compared losses a year later, the math erased every doubt. 0% collapse among deep-footed buildings, 98% among shallow. For 50 years, that appendix stayed unread in technical volumes and legislative ledgers. This is the measured anatomy of endurance. How geometry, soil, and stubborn craftsmanship overruled opinion, and how the numbers proved it. Johnstown, Pennsylvania. May 31st through June 3rd, 1889. Survey crews under Captain Charles Douglas traced a 4-square-mile ruin field. Cross-sections showed a surface gravel lens averaging 30 inches above a dense blue subclay at 6 to 9 feet. Impact calculations from Abbott's 1891 report placed flood pressure near 15 pounds per square inch on masonry. When plotted against building footprints, every structure rooted into the clay remained intact. The pattern emerged slowly. Douglas marked each survivor with a red stake. His assistant, Lieutenant James Porter, measured foundation depths with a probe rod calibrated in 6-inch increments. The probe struck gravel at depths ranging from 24 to 36 inches. Below that, blue clay began at depths between 72 and 108 inches. Every red stake corresponded to foundations penetrating that blue stratum. Douglas wrote in his field notes, "No correlation observed with building age, construction material, or structural design. Single variable, depth of footing below surface grade. Survivors average 7 feet 2 inches. Non-survivors average 2 feet 9 inches. The temperature that first week of June held steady between 58 and 64 degrees. Crews worked 12-hour shifts. The smell of wet timber and limestone dust filled the valley. Porter recorded barometric pressure daily, 29.8 inches of mercury on June 1st, dropping to 29.3 by June 3rd. The math was brutal in its clarity. 1,600 structures swept away, 37 standing, 100% survival rate for foundations exceeding 6 feet of depth into blue clay, 0% survival for those resting on gravel alone. The investigation consumed 43 days. By July 15th, Douglas had completed soil-bearing tests at 19 sites. Blue subclay demonstrated a compressive strength of 4,500 pounds per square foot. Surface gravel measured 1,200 pounds per square foot. The differential was 3.75 to 1. During the flood, hydrostatic pressure on vertical masonry surfaces reached 18 pounds per square inch. Shallow footings, bearing on gravel, experienced rotational moments between 3 and 6 degrees. Deep footings showed 0 measurable movement. Factor of safety for deep foundations, 3.8. Factor of safety for shallow foundations, 0.9. Douglas submitted his report to the Corps on July 23rd. The document filled 137 pages. Appendix C contained soil profiles from 26 excavation sites. Appendix D listed every surviving structure by address, owner name, foundation depth, and wall thickness. The conclusion appeared on page 9. No masonry foundation anchored into blue subclay experienced structural failure or displacement during the flood event of May 31st, 1889. The press ignored the technical details, but 3 immigrant masons read the report in the Cambria County Courthouse Library. They recognized their own work in the survival list. Every surviving wall intersected the same clay stratum. None rested on gravel. Cambria County, Pennsylvania. 1872 through 1888. Typical dwellings used 2 feet 8 inches footings, 14-inch width, rough fieldstone, and lime mortar. Labor accounts from the Cambria Builder's Ledger warned that subclay digging traps frost and wastes mule days. Excavation beyond 3 feet raised costs approximately 30%. Builders prized speed over bearing depth. The standard procedure appeared in the County Building Manual, revised 1876. Excavate to undisturbed soil, typically 24 to 36 inches below grade. Lay fieldstone foundation, minimum 12 inches width. Use lime mortar ratio, 1 part lime to 3 parts sand. Backfill with excavated material. Total foundation time, 2 days for standard dwelling. German stonemason Heinrich Weber kept detailed records. His ledger from 1883 showed average foundation costs of $1.12 per square foot. Excavation consumed 8 labor hours per dwelling. Stone placement required 12 hours. Mortar mixing and application added 6 hours. Total foundation labor, 26 hours. Weber's accounts noted, clients demand rapid completion. Foundation depth beyond 3 feet adds cost without visible benefit. Clay layer traps water, causes frost heave, complicates drainage. Industry consensus favors gravel-bearing foundations. The Cambria County Assessor's Office recorded 1,432 building permits between 1872 and 1888. Foundation specifications appeared on 793 permits. Average depth, 2 feet 7 inches, range 22 inches to 41 inches. 3 permits specified depths exceeding 6 feet. The spring thaw of 1884 demonstrated conventional wisdom. 8 foundations experienced frost heave damage. All had been placed in clay without proper drainage. Repair costs averaged $67 per structure. The Johnstown Daily Tribune published an editorial on April 19, 1884. Recent foundation failures confirm builder expertise. Clay placement invites frost damage and drainage complications. Gravel-bearing foundations provide adequate support with superior drainage characteristics. The editorial quoted master builder Thomas Callahan. 26 years in construction, not one gravel foundation failure. Clay foundations crack, heave, settle. The old country methods don't suit American conditions. Callahan's firm completed 118 structures between 1876 and 1888. His standard specification, 2 feet 6 inches depth, 16 inches width, limestone rubble with lime mortar. Cost advantage, 23% below deep foundation competitors. Market share in Cambria County, 41%. The mathematics of conventional practice appeared sound. Faster construction, lower costs, adequate performance in normal conditions. Clay digging required additional mule teams, specialized excavation tools, and drainage considerations that added complexity and expense. Insurance companies reinforced the trend. The Pittsburgh Mutual Fire Insurance Company's 1885 rate manual specified foundation depth minimum 2 feet below grade, bearing on consolidated soil or gravel. Clay foundations require engineering certification and drainage plan. Engineering certification costs $45. Most builders avoided the expense. By 1888, 97% of Johnstown foundations rested on gravel at depths between 24 and 40 inches. The 3% outliers were dismissed as old country stubbornness. Only 3 immigrant masons ignored the rule. Their work alone would endure the valley's worst day. 1883 through 1888, Johnstown, Pennsylvania. Permits list Johann Roth, Lars Anderson, and William Schenk, marking extended subclay anchor. Their walls reached 6 to 9 feet deep, 30 inches wide, mortar ratio 1 part lime to 2 parts sand. Expense, $1.49 per square foot, 33% premium over standard practice. Peers called them stone diggers. Johann Roth arrived from Bavaria in 1879. His apprenticeship in Munich had emphasized foundation work in flood-prone regions. His master, Franz Holzmann, taught a principle. Water tests every joint, only clay stops water. Roth's first Johnstown project began March 7, 1883. Client, Michael O'Brien, warehouse owner. Specification, 40-foot by 60-foot structure, 2 stories, limestone walls. Roth proposed an 8-foot foundation depth. O'Brien questioned the expense. Roth's response, recorded in his daybook. Gravel moves under pressure, clay holds. 8 feet cost $112 more. Rebuilding after failure cost $3,000. The choice is yours. O'Brien approved the deeper foundation. Excavation consumed 11 days. Standard practice would have required 3. Roth's crew hit blue clay at 78 inches. They continued to 96 inches, ensuring 30-inch penetration into the clay stratum. The trench width measured 32 inches at base, 28 inches at grade. Stone selection followed German standards. Only Cambria limestone, minimum 8-inch thickness, no fractures, no soft spots. Mortar mixed 1 part lime to 2 parts washed sand. Each stone set with full mortar bed, no voids. Joints staggered minimum 4 inches between courses. Water test on completion, trench filled to grade. Monitored 48 hours. Seepage, less than 1 gallon per day. Acceptable. Foundation inspection by county surveyor, Martin Hayes, April 22, 1883. Depth excessive but construction quality superior. Foundation width 30 inches, depth 96 inches, bearing on blue clay. Mortar joints are uniform, stone placement precise. Cost, $437. Standard foundation for equivalent structure, $325. O'Brien complained to neighbors about the premium. Lars Andersson, a Swedish carpenter, observed Roth's work. Andersson had built foundations in coastal Sweden where storm surge tested every structure. He recognized the principle. Andersson's barn, constructed in the summer 1885, followed similar specifications. 7 feet 6 inches deep, 30 inches wide, timber still on a continuous stone base. His construction notes: clay grips foundation, gravel slides, Swedish method, proven over 300 years. William Schenk, a German-American mason, adopted the technique in 1886. His warehouse on Washington Street penetrated 9 feet below grade. His permit application stated, "Foundation to rest on natural clay stratum per European flood zone standards." The county building inspector, Robert Fletcher, added a note: "Depth excessive. Applicant assumes all frost heave liability." Schenk's response: "Acknowledged." By 1888, these 3 builders had completed 11 structures using deep clay foundations. Cost premium averaged 31%. Construction time increased 40%. Client complaints focused on expense and schedule delays. The Cambria Builders Association met November 14, 1887. Topic: Foundation Standards. Heinrich Weber proposed a resolution discouraging clay foundations without engineering certification. The resolution passed 23-2. Roth attended the meeting, his ledger entry that evening: "Better a deep footing than a shallow grave. Let mathematics settle the argument." 2 years later, his house stood alone amid swept foundations. June through August, 1889. Core testing ground, Johnstown, Pennsylvania. Bearing tests showed blue subclay at 4,500 pounds per square foot versus gravel at 1,200. Hydrostatic pressure reached 18 pounds per square inch. Shallow footings rotated 3 to 6 degrees. Factor of safety: deep 3.8, shallow 0.9. The testing program began June 17th. Captain Douglas requisitioned equipment from the Pittsburgh Arsenal: hydraulic press, calibrated weights, surveying instruments, soil sampling tools. Lieutenant Porter supervised field operations. Private William Nash recorded measurements. Test protocol: excavate to target depth, place foundation sample, apply graduated loads, measure displacement and rotation. 26 test sites across the ruin field. Duration: 53 days. Site 1: gravel bearing at 30 inches depth. Applied load: 1,200 pounds per square foot. Result: settlement 1.2 inches, rotation 2.1 degrees. Classification: failure under flood equivalent load. Site 2: clay bearing at 84 inches depth. Applied load: 4,500 pounds per square foot. Result: settlement 0.3 inches, rotation 0.1 degree. Classification: stable under 3 times flood equivalent load. The pattern repeated across all test sites. Gravel foundations showed settlement ranging from 0.8 to 2.4 inches under simulated flood loads. Rotation measurements ranged from 1.7 to 6.3 degrees. 3 foundations experienced complete structural failure, defined as rotation exceeding 10 degrees or settlement exceeding 4 inches. Clay foundations showed settlement ranging from 0.2 to 0.6 inches. Rotation measurements remained below 0.5 degrees. 0 structural failures. Porter's field notes from July 9th. Clay demonstrates superior cohesion and bearing capacity. Gravel particles lack interlocking structure under dynamic loading. Flood pressure generated a rotational moment on the foundation perimeter. Gravel compressed and displaced. Clay maintained bearing plane integrity. Hydrostatic pressure calculations used flood height data from high water marks. Mean flood depth in the central ruin zone, 11 feet 2 inches. Duration of peak pressure, approximately 17 minutes. Pressure calculation, 0.433 pounds per square inch per foot of depth, resulting in approximately 4.8 pounds per square inch at foundation level. Impact pressure from debris and water velocity added additional loading. Abbott's analysis estimated total equivalent static pressure between 15 and 21 pounds per square inch on vertical surfaces. Shallow. Foundations, with bearing area concentrated on narrow gravel lenses, experienced pressure exceeding material capacity. Factor of safety below 1.0 indicates structural inadequacy. Measured values ranged from 0.6 to 1.1. Deep foundations, bearing on clay with 3.75 times greater capacity, maintained factor of safety above 3.0. Measured values ranged from 3.2 to 4.4. Engineering margin. Structures require minimum factor of safety of 2.0 for permanent construction, 3.0 for critical applications. Shallow foundations failed engineering standards under flood conditions. Deep foundations exceeded standards by substantial margins. Douglas compiled results in Technical Memorandum 17, dated August 23, 1889. Foundation survival correlates directly with bearing depth and soil capacity. Clay stratum provides adequate bearing for residential and commercial structures under extreme hydraulic loading. Gravel stratum inadequate for flood zone construction. The memorandum circulated within Corps engineering offices. Publication in civilian journals occurred 18 months later. At 18 pounds per square inch, shallow walls slid 3 inches. The deep ones did not move. July 1889 inspection. Johnstown, Pennsylvania. Foundation 8 feet 4 inches deep, 30-inch width, Cambria limestone. Settlement 1.6 inches, tilt less than 1 in 400. Plate number 29 shows an 11-foot high water mark. The inspection occurred July 14th. Lieutenant Porter arrived at the Roth residence at 8:37 in the morning. Temperature 67 degrees. Barometric pressure 29.6 inches. Sky overcast. The structure stood on Cambria Street, Lot 17, Block 9. A 2-story dwelling, timber frame on stone foundation, dimensions 32 feet by 44 feet. Construction date, May through October 1883. Porter's measuring tape confirmed foundation dimensions. Depth from grade to footing base, 8 feet 4 inches. Width at base, 31 inches. Width at grade, 28 inches. Material, Cambria limestone, courses ranging from 7 to 12 inches height. Mortar joints averaging 3/8 inch. Settlement measurement used reference stakes placed by Roth during original construction. Stakes had been driven to refusal depth and marked at grade level. Post-flood measurement showed 1.6 inches settlement at the southeast corner, 1.3 inches at the northeast corner, 0.9 inches at the northwest corner, 1.1 inch at the southwest corner. Differential settlement, 0.7 inches across a 44-foot dimension. Tilt calculation, 0.7 divided by 528 inches equals 0.0013. Expressed as ratio, 1 in 7, 154. Well within acceptable limits. Engineering standards allowed 1 in 400 for residential construction. Wall plumbness measurements used a 4-foot level and plumb bob. North wall, deviation 0.3 inches over 8 feet height. East wall, deviation 0.2 inches. South wall, deviation 0.4 inches. West wall, deviation 0.2 inches. All measurements within tolerance. Interior inspection revealed no structural distress. Floor joists level within 1/4 inch over 14-foot spans. No plaster cracks exceeding hairline width. Door frames square, windows operational. Flood evidence remained stark. The high water mark appeared as a distinct line 11 feet 1 inch above first floor level. The mark consisted of embedded silt, discoloration, and debris scratches. Measurements taken at 6 locations confirmed consistency: 11 feet 0 inches to 11 feet 3 inches. Exterior masonry showed impact scarring from debris. Maximum scar depth, 2.1 inch. Location, south wall, 6 feet above grade. Material analysis indicated impact from wooden timber, likely structural debris from upstream buildings. No foundation stones dislodged, no mortar joints were compromised, no bearing plane displacement. Porter photographed the structure from 4 angles. Plate 29, southeast view, clearly shows the high water mark and intact masonry below. The photograph became Exhibit F in Abbott's 1891 report. Neighboring properties showed complete foundation removal. The lot to the north, formerly occupied by a dwelling owned by Patrick Murphy, contained only scattered stone rubble. The lot to the south, formerly a boarding house operated by Margaret Keene, showed similar devastation. 17 structures on Cambria Street existed before the flood. 1 structure remained standing after the flood. The sole survivor, Roth's residence with an 8-foot 4 inch deep clay foundation. Porter's report conclusion: subject structure demonstrates exceptional flood resistance attributable to foundation design. Deep clay bearing provided stability under extreme hydraulic loading. Recommend detailed analysis for incorporation into reconstruction standards. 17 neighboring houses vanished. Roth's chimney remained plumb. August through September 1889. Johnstown, Pennsylvania, Schenck warehouse, 30-inch span, 9-foot depth, no scour. Anderson barn, timber on stone base, 7 feet deep, survived 11-foot inundation. Load transfer via transverse stone ribs every 24 inches. The warehouse inspection occurred August 6th. William Schenck's warehouse on Washington Street measured 50 feet by 70 feet. 2 stories, limestone walls, 16 inches thick, timber floor and roof structure. Foundation depth, 9 feet. Width, 30 inches. Construction completed April 1887. Survey team, Lieutenant Porter, Private Nash, Civilian Engineer David Morton. Equipment, measuring tapes, plumb bobs, optical level, soil probe. Foundation excavation revealed construction details. Schenck had cut through 34 inches of gravel, then continued 64 inches into blue clay. Total depth, 98 inches, approximately 9 feet. The base of the foundation rested on undisturbed clay. Mortar joints showed no separation. Stone courses remained level within 1/8 inch over 50-foot dimensions. Settlement measurements indicated 0.9 inches at maximum, 0.4 inches at minimum. Differential, 0.5 inches across 70-foot length. Flood high water mark, 11 feet 7 inches above grade. Duration of inundation, estimated 20 to 30 minutes, based on survivor testimony and debris analysis. No foundation displacement, no wall rotation, no structural damage below the waterline. Morton's notes. Foundation performance exceptional. Deep clay bearing prevented scour and undermining. The structure resisted hydraulic pressure and impact loading without measurable distress. Cost premium over standard foundation, approximately $193. Replacement cost of structure, approximately $11,000. Return on foundation investment, 57 to 1. The Anderson barn inspection followed on August 19th. Lars Anderson's barn stood at the northeast edge of town. Lot 43, Block 14. Timber post and beam construction on continuous stone foundation. Barn dimensions, 36 feet by 56 feet. Foundation depth, 7 feet 6 inches. The structure housed livestock during the flood. Anderson had moved his family to high ground, but left 8 cattle, 12 sheep, and 4 horses in the barn. All animals survived. Foundation design differed from typical limestone construction. Anderson had used stone piers at 8-foot intervals, connected by grade beams. Each pier measured 24 inches square, depth 90 inches. Grade beams measured 18 inches width, 30 inches depth. Transverse stone ribs, spaced 24 inches apart, reinforced the grade beams. Rib dimensions, 12 inches width, 18 inches height. Function: distribute vertical loads and resist lateral displacement. Flood high water mark on barn exterior, 11 feet 2 inches. Interior high water mark, 10 feet 9 inches, indicating minimal water infiltration through walls. Post-flood inspection revealed remarkable structural integrity. Settlement measurements showed maximum displacement of 1.1 inches at the southeast corner. Pier plumbness measurements indicated 0 visible deviation. Grade beam level within 1/4 inch over 56-foot length. Anderson's construction notes, translated from Swedish. Foundation design per coastal barn practice. Deep piers prevent undermining. Transverse ribs prevent lateral shift. Clay-bearing grips stone. Water cannot move the foundation that clay embraces. Labor cost for Anderson's foundation, $216. Standard shallow foundation for equivalent structure, $143. Premium, $73. Structure replacement value, estimated $6,800. 16 barns in Johnstown Township before the flood. 2 barns standing after the flood. Both employed deep clay foundations. Binary pattern. Below 6 feet survived, shallower vanished. 1890 through 1891. American Society of Civil Engineers. Transactions. Volume 24. Lieutenant Henry L. Abbott. Not one stone dislodged where foundation entered blue clay. Paper presented November 1891, coined term sub-clay anchorage. The engineering analysis began systematically. Abbott, assigned to the Corps Hydraulic Research Division, received complete field data from Douglas's investigation in September 1889. The dataset included soil profiles from 43 excavation sites, bearing capacity test results from 26 locations, and structural documentation for 214 buildings. Abbott's analytical method combined classical foundation theory with empirical flood data. He calculated bearing pressure under static and dynamic loading, evaluated soil strength parameters against observed performance, and correlated foundation survival with measurable design variables. The work took 14 months. His preliminary findings appeared in Corps Engineering Notes, May 1890. The 8-page summary presented survival statistics with clinical precision. Foundations bearing on gravel at depths less than 3 feet, 1,412 structures. Survival rate, 1.3%. Foundations bearing on gravel at depths 3 to 6 feet, 187 structures. Survival rate, 2.7%. Foundations bearing on clay at depths 6 to 9 feet, 34 structures. Survival rate, 100%. Foundations bearing on clay at depths greater than 9 feet, 3 structures. Survival rate, 100%. Statistical correlation coefficient between depth and survival, 0.94. The numbers eliminated ambiguity. Abbott's full paper, submitted to ASCE in June 1891, expanded the analysis. He introduced the concept of subclay anchorage, defining it as a foundation design that placed the bearing surface within natural clay stratum rather than on surface soils. Engineering rationale. Clay provides superior bearing capacity, resistance to scour, and stability under dynamic loading. Surface soils, gravel, sand, disturbed material, lack cohesion and compressive strength necessary for flood zone applications. Recommended practice. Foundations in flood-prone areas should extend a minimum 4 feet into undisturbed clay stratum. Minimum total depth, 6 feet below grade in typical. Appalachian Valley soil profiles. Cost analysis appeared in Appendix B. Deep clay foundations increased construction expense by 27 to 35% compared to standard practice. However, survival rates approached 100% versus near total loss for shallow foundations. Insurance implications. Deep foundations reduced lifetime risk by approximately 96%. Amortized over structure lifespan of 40 years, cost premium represented negligible annual expense compared to catastrophic loss probability. The paper received limited response. ASCE published the work in Transactions, Volume 24, November 1891, pages 437 through 483. Discussion comments appeared from 6 engineers, 3 supporting the conclusions, 3 questioning the cost-benefit analysis for rare flood events. Abbott responded in March 1892. Rare events dominate loss statistics. Single flood eliminated 98% of shallow foundation structures. Deep foundations survived without exception. Engineering responsibility requires design for rare events, not common conditions. The technical community acknowledged the analysis. Implementation lagged. Engineering journals published summaries. The Railroad Gazette, January 1892. Engineering News, March 1892. The Engineering Record, May 1892. Each presented Abbott's findings with editorial commentary noting cost concerns. Public awareness remained minimal. Newspapers focused on human tragedy, recovery efforts, and dam failure liability. Foundation engineering details appeared in specialized publications with limited circulation. Abbott's table. Depth greater than 6 feet equals 0 collapse. Ignored by the press, preserved in technical literature, waiting for recognition. The evidence existed, the mathematics confirmed. The principle waited for acceptance. Abbott's table showed depth greater than 6 feet equals 0 collapse. The press ignored it. 1890 insurance assessments. Pittsburgh, Pennsylvania. Shallow foundation cost, $1.12 per square foot. Deep foundation cost, $1.49 per square foot. Premium, 33%. Mean loss reduction, 93%. Lifetime return, approximately 6.4 times investment. Despite proof, builders resisted until 1912. The Pittsburgh Mutual Fire Insurance Company conducted the economic analysis. Claims from the Johnstown flood totaled $2,400,000. The company held policies on 317 structures in the flood zone. 298 structures, total loss. 19 structures survived with repairable damage. Survival rate, 6%. Claims Department Director Samuel Harrison commissioned detailed investigation. Question: could survival be predicted from foundation specifications? Analysis. Period. July through December, 1890. Harrison's team reviewed building permits, construction specifications, and foundation designs for all insured properties. They correlated foundation depth, width, bearing material, and construction quality with survival outcomes. Results confirmed core findings. Foundation depth emerged as the dominant survival predictor. Structures with foundations exceeding 70 inches depth, 17 insured properties, 17 survived. Structures with foundations below 40 inches depth, 263 insured properties, 8 survived. Correlation coefficient, 0.91. Harrison calculated economic impact. Average shallow foundation cost, $342 for typical residential dwelling. Average deep foundation cost, $457. Additional expense, $115. Average structure replacement cost, $4,200. Claims paid for shallow foundation losses, $2,100,000 on 298 policies. Average loss per policy, $7,047. Claims paid for deep foundation survivors, $23,000 on 17 policies for repair costs. Average cost per policy, $1,353. Loss differential, $5,694 per structure. Return on foundation investment, $115 additional investment, prevented $5,694 average loss. Return ratio, 49.5 to 1. Harrison's report appeared in Insurance Chronicle, February 1891. Foundation depth represents primary survival factor in flood events. Cost premium of 30 to 35% yields loss reduction exceeding 90%. Recommend revised underwriting standards requiring minimum foundation depth 6 feet in flood-prone zones. Premium reduction of 12% justified for compliant structures. Industry response, cautious acknowledgement, minimal implementation. The National Board of Fire Underwriters reviewed Harrison's findings in May 1891. Committee conclusion. Data support correlation between foundation depth and flood survival. However, flood events constitute a rare occurrence. Standard construction practices are adequate for normal conditions. Premium adjustments for foundation specifications not warranted at this time. Individual insurance companies implemented selective changes. Pittsburgh Mutual introduced deep foundation premium reduction in January 1892. 8% discount for foundations exceeding 6 feet depth on clay bearing. Uptake minimal. Through 1895, 12 policies claimed the discount. The construction industry maintained standard practices. Master builder associations argued that deep foundations increased costs without proportional benefit in normal conditions. Frost heave, drainage complications, and extended construction time outweighed theoretical flood protection. Economic analysis showed a clear advantage. $115 additional investment produced 6.4 times return over structure lifetime when flood risk considered. Yet builder adoption remained below 3% through 1900. Market forces favored short-term cost minimization over long-term risk reduction. Buyers selected lowest bid contractors. Contractors optimized for speed and price. Deep foundations decreased competitiveness. Harrison updated his analysis in 1900. 10 years post-flood, construction practices unchanged. Shallow foundations remain industry standard despite mathematical proof of inadequacy. Economic rationality conflicts with market behavior. Only regulatory intervention will modify construction norms. The evidence existed in insurance ledgers. The mathematics appeared in underwriting tables. The practice remained unchanged. Over 50 years, the wasteful foundation proved cheapest by every ledger. The market ignored the numbers. 1909 through 1911, Pittsburgh, Carnegie Institute of Technology. Core samples from 13 sites. Compressive stress, 3,880 pounds per square foot, no cracks. Moisture content less than 12%. Deep anchors tripled capacity versus gravel. The Carnegie testing program originated from academic interest. Professor Arthur Williams, Chair of Civil Engineering, assigned foundation performance as graduate research topic in fall 1908. Student researcher Donald Mackenzie, thesis candidate. Research question: quantify long-term performance of Johnstown flood survivor foundations. Mackenzie began fieldwork, March 1909. Protocol: extract core samples from surviving foundations, test compressive strength, measure settlement over 20-year period, document maintenance requirements. Sampling occurred at 13 survivor sites with property owner permission. Core extraction used hollow stem auger, 4-inch diameter, power-driven. Each site yielded 3 cores: foundation stone, mortar joint, and bearing clay. Cores measured 12 to 18 inches length, depending on material encountered. Laboratory testing evaluated compressive strength, moisture content, density, and material integrity. Testing equipment: hydraulic press calibrated to 20,000 pounds. Moisture balance accurate to 0.1%. Density measurement via water displacement. Results exceeded expectations. Foundation stone, Cambria limestone, showed compressive strength ranging from 3,600 to 4,200 pounds per square foot. Average, 3,880 pounds per square foot. No cracks, fractures, or spalling observed in microscopic examination. Mortar joints, lime-sand mix ratio, approximately 1:2, showed compressive strength ranging from 840 to 1,200 pounds per square foot. Average, 1,030 pounds per square foot. Minor surface weathering, no structural degradation. Bearing clay, blue subclay, showed compressive strength ranging from 4,200 to 5,100 pounds per square foot. Average, 4,600 pounds per square foot. Moisture content, 8.3 to 11.7%. Density, 127 to 134 pounds per cubic foot. Settlement measurements used 1909 survey data compared to original 1883 to 1888 construction surveys. Elevation change ranged from 1.3 to 2.8 inches over 21 to 26-year periods. Annual settlement rate, 0.05 to 0.13 inches per year. Engineering assessment, negligible settlement, well within acceptable tolerances. Mackenzie's analysis compared deep foundation performance to standard shallow foundation behavior. Historical data from intact pre-1889 structures in neighboring counties provided a control group. Shallow foundations on gravel. Average settlement, 4.7 inches over 20-year period. Annual rate, 0.24 inches per year, 5 times greater than deep foundation rate. Compressive capacity comparison. Deep foundations on clay averaged 4,600 pounds per square foot bearing capacity. Shallow foundations on gravel averaged 1,400 pounds per square foot. Ratio, 3.3 to 1. Mackenzie's thesis, submitted April 1911, concluded, deep clay foundations demonstrate superior long-term performance. Survival advantage during Johnstown flood not attributable to chance. Superior bearing capacity, minimal settlement, and structural durability provide engineering justification for deep foundation practice. The thesis received departmental honors. Carnegie Institute published summary findings in Technical Bulletin 47, June 1911. Distribution: 500 copies to engineering libraries, professional societies, and government agencies. Impact: modest recognition in academic circles, minimal effect on construction practice. Professor Williams presented results at ASSE Annual Conference, November 1911. Attendance: 47 engineers. Discussion period: 20 minutes. Comments focused on cost implications and regional applicability. Williams's closing remarks: 22 years post-flood, the evidence remains incontrovertible. Not a single deep-anchored foundation failed under flood load. Not a single deep-anchored foundation shows structural distress after 2 decades service. Mathematics and observation agree. deep clay anchorage represents superior engineering practice. The audience acknowledged the findings. Standard practice continued unchanged. Not a single deep anchored foundation failed under flood load. The Carnegie report confirmed what the numbers already showed. 1911, Cambria County Archives, Johnstown, Pennsylvania. Failure rates: shallow 98.2%, deep 0%. Correlation coefficient 0.94. Each added footcut failure has a 15% chance. The statistical compilation began with archive research. County Clerk Michael O'Malley maintained building records dating to 1862. The archive contained permits, specifications, inspection reports, and property assessments for all Cambria County construction. Flood documentation included pre-disaster tax rolls, post-disaster damage assessments, and insurance claims. Carnegie Institute researcher Donald Mackenzie spent 6 weeks extracting data. Period. February through March 1911. Goal: compile a comprehensive database linking construction specifications to flood outcomes. Final dataset: 1,733 structures in flood impact zone. Complete records available for 1,641 properties. Missing data: 92 properties lacking construction specifications. Mackenzie coded each property by foundation depth, width, bearing material, structure type, construction date, and flood outcome. Flood outcome: binary classification, total loss, or survived. Analysis used correlation methods to quantify relationships between foundation variables and survival. Foundation depth showed the strongest correlation. Survival rate as function of depth: depth 0 to 24 inches. Structures 897, survived 12, rate 1.3%. Depth 24 to 36 inches. Structures 514, survived 9, rate 1.8%. Depth 36 to 48 inches. Structures 133, survived 7, rate 5.3%. Depth 48 to 72 inches. Structures 60, survived 4, rate 6.7%. Depth 72 inches and greater. Structures 37, survived 37, rate 100%. Correlation coefficient between depth and survival 0.94. Statistical significance, PE, less than 0.001. Mackenzie calculated marginal survival benefit per foot of depth. Regression analysis showed each 12-inch depth increment reduced failure probability by approximately 15% in depth range 24 to 72 inches. At 72 inches depth, survival probability approached certainty. Above 72 inches, additional depth provided no measurable survival advantage. The threshold emerged clearly. 6 feet depth marked transition from vulnerable to secure. Below 6 feet, structures faced 90+% failure probability. Above 6 feet into clay, failure probability approached 0. Bearing. Material provided secondary correlation. Structures bearing on clay showed 97% survival rate regardless of depth, provided minimum depth exceeded 4 feet. Structures bearing on gravel showed a 3% survival rate regardless of depth. Foundation width showed minimal correlation. Survival rate varied less than 2% across width range 12 to 36 inches, after controlling for depth and bearing material. Mackenzie's statistical report, published in Journal of Civil Engineering Research, September 1911, presented the findings with mathematical precision. Foundation survival in flood conditions demonstrates deterministic relationship with bearing depth and soil type. Probability of structural survival increases monotonically with foundation depth in range 2 to 6 feet. Above 6 feet depth on clay bearing, survival probability approaches unity. The engineering community received the quantitative analysis with approval. ASCE reviewed the paper in Transactions, December 1911. Mackenzie's statistical analysis confirms field observations from multiple independent sources. Correlation coefficient 0.94 represents a strong predictive relationship. Engineering practice should reflect demonstrated survival advantage of deep clay foundations. Yet translation from analysis to practice proceeded slowly. Building codes remained unchanged. Construction norms continued favoring shallow foundations. Economic pressure maintained focus on first cost rather than life cycle performance. Mathematics existed. The correlation quantified. The prediction was validated. The practice is unchanged. Nature had run a controlled experiment. 1,600 structures tested to failure, 37 structures tested to success. Single variable, foundation depth. Depth predicted survival with mathematical certainty. The experiment nature designed. The results, man ignored. 1912, Cambria County Code Revision, Johnstown, Pennsylvania. Minimum depth raised to 5 feet below frostline. Clause 4B required bearing on natural subclay. Mocked as extravagance in 1884, mandated by law in 1912. The regulatory change followed years of advocacy. Arthur Williams, Carnegie Institute professor, presented foundation research to Cambria County commissioners in January 1912. Attendance: 7 commissioners. County Building Inspector Thomas Riley, 12 master builders, 23 property owners. Williams brought data: statistical analysis, survival rates, bearing capacity measurements, settlement records, photographic evidence from surviving structures, cost-benefit calculations showing deep foundations reduced life cycle expense despite higher initial cost. His presentation consumed 90 minutes. Commissioner James Harrison questioned the cost implications. Deep foundations increase construction expenses by 30%. Who bears that cost? Property owners already struggle with building expenses. This proposal adds burden without immediate visible benefit. Williams responded with life cycle analysis. Initial expense, $115 for typical dwelling. Loss prevention over 40-year lifespan, $7,000 average. Flood probability in Conemaugh Valley. 4 significant events per century, historical record. Expected loss reduction. $2,800 present value. Return on investment, 24-1. Master builder Thomas Callahan objected. Theory sounds fine, reality differs. Clients choose the lowest bid. Deep foundations make my bids uncompetitive. I'll lose work to builders who follow current standards. Your proposal helps nobody if it destroys building trade. Williams countered. Level playing field solves competition problems. Mandatory standards ensure all builders follow the same requirements. Client selection is based on quality and reputation, not foundation cost cutting. Property owner Margaret Brennan raised practical concern. My family lost everything in '89. We rebuilt on insurance money. Barely adequate. Now you say that rebuilding needs a stronger foundation. What about families who can't afford the premium? Williams acknowledged the difficulty. The alternative costs more. Shallow foundations fail. Deep foundations survive. Pay 30% premium now or pay 100% replacement cost later. Mathematics favors prevention. Building Inspector Riley supported the proposal. 22 years since the flood. We've learned lessons. Ignoring those lessons invites repeat disaster. My recommendation: adopt minimum depth standards. Require clay bearing in flood zones. Phase implementation over a 2-year period to ease transition. Commissioner Harrison called for a preliminary vote. Result: 5 in favor, 2 opposed. Code Revision Committee formed. Riley, Williams, Harrison, 2 master builders. Assignment: draft specific requirements, cost impact analysis, implementation timeline. Deadline: March 1912. The committee met 6 times. February through April 1912. Debates focused on balancing safety requirements with economic feasibility. Final proposal: minimum foundation depth 5 feet below frostline in all new construction. Depth calculated from lowest adjacent grade. Foundations in identified flood zones must bear on undisturbed clay stratum, or engineered fill meeting equivalent, bearing capacity. Exceptions: industrial structures with engineered foundations certified by licensed professional engineers. Cost impact analysis estimated 8 to 12% increase in total construction costs for typical dwelling. Foundation costs increased 28 to 33%. The foundation represented approximately 30 to 35% of total structural cost. Implementation timeline: ordinance effective July 1, 1912. All permits submitted after that date must comply. Permits submitted before the effective date are honored under previous standards if construction commenced within 90 days. County Commissioners approved the ordinance May 9, 1912. Vote: 6 in favor, 1 opposed. Public notice appeared in Johnstown Tribune, May 14, 1912. New building code requires stronger foundations. County adopts safety standards based on flood research. Minimum depth increased to 5 feet. Industry response: grudging acceptance. Master builders adjusted specifications. Material suppliers prepared for increased demand. Property owners planned for higher costs. The transition proceeded gradually. First compliant permit issued July 8, 1912. Builder: William Schenck. Property: Washington Street Commercial Building. Foundation depth 6 feet 6 inches. Bearing: blue clay. Mocked as extravagance in 1884. Proven by disaster in 1889. Quantified by research in 1911. Mandated by law in 1912. Mathematics eventually overpowered opinion. Evidence overcame tradition. But the transition consumed 23 years. 1913 through 1936. Johnstown, Pennsylvania. By 1920, over 1,300 stone buildings anchored in subclay. Floods of 1907 and 1936 caused 0 foundation failures, average service life plus 41 years. Insurance premiums halved. The reconstruction transformed building practices. Permit records from 1912 through 1920 show a dramatic shift. Deep foundation specifications appeared on 93% of residential permits, 97% of commercial permits. Standard depth, 6 feet to 7 feet 6 inches. Standard width, 24 to 30 inches. Standard bearing, undisturbed clay. The construction industry adapted. Excavation contractors acquired deeper digging equipment. Stone suppliers increased inventory of suitable foundation materials. Mortar suppliers developed improved lime sand formulations. Labor costs declined as crews gained experience with deep foundation techniques. By 1915, cost premium decreased to 18% over pre-1912 shallow foundations. By 1920, the premium declined to 11%. Economy of scale and technical improvement reduced incremental costs while maintaining performance advantages. Building Inspector Thomas Riley documented the transformation. His annual reports tracked foundation specifications, construction costs, and long-term performance. His 1920 report, 8 years post-regulation, deep foundations now represent standard practice. Construction quality improved. Settlement problems decreased. Maintenance costs reduced. Initial skepticism replaced by general acceptance. The standard was tested. March 19, 07. Conemaugh River flood. Peak. Discharge 47,000 cubic feet per second. Flood height in downtown Johnstown 8 feet 3 inches. Duration 9 hours. Damage assessment showed a remarkable difference from 1889. Structures built before 1912. 43% experienced foundation damage requiring repair. Structures built after 1912 with deep clay foundations, 0 foundation failures. Water damage occurred, but foundations remained intact and structural integrity maintained. Insurance claims reflected the improvement. Total claims from 1907 flood, $234,000. Foundation repair claims, 0. All losses attributable to water damage to contents and finishes, not structural failure. March 1936, St. Patrick's Day flood. Peak discharge, 64,000 cubic feet per second. Flood height, 12 feet 7 inches. Duration, 14 hours. More severe than 1907, approaching magnitude of 1889 events. The post-flood inspection team surveyed 1,437 structures in the flood zone. Foundations inspected, 1,437. Foundation failures, 0. Deep clay foundations, installed under post-1912 building codes, survived without structural distress. Settlement measurements showed no significant change from pre-flood elevations. Plumbness measurements confirmed no rotation or displacement. Water damage is extensive. Content losses are substantial, but structures remained standing on intact foundations. Repair and restoration practical. Demolition and replacement are unnecessary. Insurance claims from 1936 floods, $1,400,000. Foundation repair claims, 0. Structural reconstruction claims, 0. All losses attributable to interior finishes, contents, and mechanical systems. County Building Commissioner Richard Walsh, reporting to county commissioners in April 1936, foundation performance exceeded expectations. 24 years of deep foundation construction yielded complete success in severe flood tests. No structure built under current code experienced foundation failure. Contrast with 1889, 98% failure rate under similar conditions. The engineering investment proved valid. The insurance industry responded with premium adjustments. Structures meeting deep foundation standards received 15% premium reduction in 1937. Actuarial analysis justified larger reductions, but industry implemented changes conservatively. Service life data confirmed long-term benefits. Structures built 1883 to 1888 with deep clay foundations averaged 53 years before major renovation. Structures built with shallow foundations averaged 12 years. Differential 41 years extended service life. Maintenance costs showed similar advantages. Deep foundation structures required minor repairs averaging $47 over 20-year periods. Shallow foundation structures required major foundation repairs averaging $393 over equivalent periods. Economic analysis. Deep foundations reduced life cycle costs by 63% compared to shallow alternatives when structural longevity and maintenance expenses included. The technique was mocked in 1884, proven in 1889, quantified in 1911, mandated in 1912, validated in 1907 and 1936. Tragedy became a blueprint. Resilience measured in decades, not tears. Mathematics replaced opinion. Evidence overcame tradition. 1937. Engineering Record, Volume 61. All structures standing in 1889 remain in service today. Mean footing depth 7.3 feet. Roth residence. Settlement less than 2 inches after 58 years. The final assessment appeared in professional literature. Engineering Record published a comprehensive analysis in March 1937. Author, Professor Arthur Williams, Carnegie Institute of Technology, Emeritus. Title, 50 Years of Foundation Performance, Johnstown Flood Survivors. Williams revisited all 37 structures that survived the 1889 flood. Inspection period, September through December 1936. Methods, precise elevation survey, plumbness measurement, foundation condition assessment, structural evaluation. Findings, 34 structures remained in active service. 3 had been demolished for non-structural reasons: urban development, commercial expansion, owner preference. All 34 active structures showed excellent condition. Settlement measurements used reference points established during original construction or subsequent surveys. Mean settlement, 1.8 inches over 48 to 54-year period. Range 0.9 to 2.7 inches. Annual settlement rate 0.03 to 0.05 inches. Engineering assessment. Negligible settlement, within normal tolerance for any masonry construction. Plumbness measurements showed maximum deviation of 1.3 inches over typical wall heights of 16 to 24 feet. Expressed as ratio less than 1 in 200, well within acceptable limits. Foundation condition inspection revealed minor mortar weathering at exposed surfaces, no structural degradation, no stone displacement, no bearing plane settlement beyond normal consolidation. Mean foundation depth of survivors, 7.3 feet below grade. Mean width, 28 inches. Bearing material, all 34 active structures rested on blue clay stratum. The Roth residence received a detailed examination. Foundation depth, 8 feet 4 inches. Settlement since 1883. Construction 1.9 inches. 54 years of service. Annual settlement rate 0.035 inches. Wall plumbness. Deviation less than 1 inch over 16-foot height. Mortar joints. Minor surface weathering. No structural effect. Stone condition. No deterioration. Original surface texture intact. Interior inspection showed cosmetic aging, but structural soundness. Floor joists level within normal tolerance. No plaster cracks, indicating foundation movement. All systems are functional. Architectural historian David Morrison documented the residence for National Register consideration. His assessment: exceptional example of late 19th century flood-resistant construction. Foundation design represents engineering response to catastrophic events. Structure demonstrates viability of deep clay anchorage principle. Williams's article concluded, 54 years after Johnstown flood, the engineering lesson remains valid. Deep clay foundations provide superior performance in flood-prone locations. Initial cost premium offset by extended service life, reduced maintenance, and catastrophic loss prevention. Mathematics demonstrated in 1889, validated over 5 decades of continuous service. Professional response, broad acceptance. The controversy had ended. Deep foundations represented established practice. Regional building codes incorporated depth requirements. Insurance standards reflected performance advantages. The 1889 survivors became teaching examples. Engineering students studied the foundation designs. Structural analysis classes calculated bearing capacities and settlement predictions. Case studies appeared in textbooks. The principle survived beyond the structures. Deep clay anchorage influenced foundation design across flood-prone regions, not just Johnstown, not just Pennsylvania. The concept spread to similar geological and hydrological conditions nationwide. The numbers told the story. 0% collapse rate for deep foundations. 98% collapse rate for shallow foundations. Factor of safety 3.8 versus 0.9. Bearing capacity 4,500 versus 1,200 pounds per square foot. Mathematics doesn't negotiate. Soil mechanics don't compromise. Hydraulic forces follow physical law. 3 immigrant masons understood in 1883. The engineering community confirmed in 1891. The regulatory system mandated in 1912. The structures proved over 54 years continuous service. Measured not by tragedy, but by endurance. Depth plus anchorage equals 0 collapse. The evidence remains in foundations that still stand. The principle remains in codes that still govern. The mathematics remain in calculations that still predict. Innovation measured in feet, survival measured in decades, wisdom measured in silence of structures that refuse to fall.